Hello everyone, welcome back to the YouTube channel. This is part one of a two-part video on fast exact simulation of the first passage event of a tempered stable subordinator. This is joint work with Van Glen, Alexander Mijatovic from the University of Warwick and the Alan Turing Institute. And this research was funded by EPSRC. So in the first part of these videos, we will show you the algorithm, the performance of the algorithm, the expected running time, and we will also show how you can use it to solve some applications. Okay, so some problems in practice. In the second part, we will instead go into the structure of the algorithm, how you can construct it, what are the difficulties, and how you can circumvent them. Okay, so the main problem at hand is to consider a non-increasing, absolutely continuous boundary B and a subordinator S. And we're interested in the first time the subordinator crosses the boundary B, the value before crossing and the value after crossing. Okay, so these characteristics are very useful and used a lot in practice. For example, in ruin theory, when you're interested in the ruin time and the penalty function. Okay, and other applications that we will discuss. Okay, so first, just to set some notation, given some alpha between 0 and 1 and some positive theta and a non-negative q, that means possibly 0, we consider a tempered stable subordinator q, under EQ or PQ, where the Laplace transform has this form and the Levy measure has this form. Okay, this is simply the notation. Then our algorithm for any such barriers B will return this vector with this with a complexity bounded by this function. So we can consider other boundary functions B. So for example, discontinuous but always non-increasing. However, certain steps become more difficult, harder to analyze, but in principle, many things can be generalized. Okay, if that's what you want to do. Now, in our algorithm for this setting, the complexity is bounded by this number, and you can see that it's at most polynomial in any of the variables. So it's at most linear in Q, B0, at most cubic in alpha as alpha goes to 1, and at most alpha alpha to the minus 2 log alpha when alpha goes to 0. Okay, logarithmic in the number of precision bits. So this is completely fine. It's only polynomial. This is very expected for distributions that become very degenerate as you take alpha to 0, 1, or you take all these parameters in some bad direction, extreme direction, okay? Though we must say that for marginals and easier variables, there exist algorithms, for example, by Dasius et al., to get the marginals in finite and uniformly bounded expected running time, okay? But in here, we're dealing with a much harder object, so it's expected to have some kind of deterioration like this. Okay, so what can you use it for? So you can solve numerically some fractional partial differential equations, FPDEs. Okay, so if you consider this FPDE, where the operator TDA is a fractional Caputo type fractional differential operator of order less than 1, acting on the variable t, and you have a generator A of x of a Feller semigroup, so for example, Brownian motion or of geometric Brownian motion, then this kind of solution has a probabilistic representation. And the probabilistic representation is this one. Okay, so step by step. Here, YS is a decreasing process started at t and stopped at the first crossing of value a. This crossing has value is denoted by tt. Okay, and x is an independent stochastic process generated by the generator AX. Okay. So, in fact, our motivation is a prior paper due to my co-authors and Vasily Kolokoltsov, where they get a Monte Carlo estimator for these kind of FPDEs when the subordinator in question, so basically the dynamics of Y, boil down to a stable subordinator. Because then it is possible to simulate Y jointly with the subordinator in a nice time grid, and it's possible to control the error. We wanted to extend such methodology to more general subordinators, so basically more general fractional operators. But no such algorithms existed, not at least the ones that have a nice control over the complexity. Okay, most algorithms, for example, this algorithm by Chi, that will work efficiently, will work, but is not efficient because it has infinite expected runtime. Okay, and for certain processes, Dasius and other collaborators also developed some kind of algorithm. But we were interested in something that works efficiently for many different kind of barriers. For example, a constant barrier for a process with a drift is equivalent to hitting a barrier that's linearly going down for a process without a drift, right? So this is exactly the kind of a problem that we're trying to solve and why we're motivated to work on this algorithm that we developed. Since the paper in this time is focused on the simulation algorithm, we will consider in this presentation a simplified version of this problem where G does not exist. Basically, G is 0. Okay. Then the stochastic representation for the FPDE only involves phi, and the Monte Carlo estimator can be written of this like this. Okay. And you can see that since simulations are exact in this situation, well, we don't have any bias. This is simple Monte Carlo, right? The complexity or the dependence of the complexity in epsilon is simply epsilon to the minus 2 if you want the L2 error to be bounded by epsilon squared. Okay? And you can do this nice antithetic coupling of the variables. That means the variables in N are in K are independent, but there's some interesting dependence in T and X. This is all standard, so you can get nice curves here as estimated solutions. Okay? And you can see that it works pretty well already for 10,000 samples, and it runs very, very quickly. In this case, we use the geometric random motion x of t, and we use the parameters that are shown on the screen. Okay, and a temperate stable subordinator, of course. So, okay, why is this so important? What's there to gain from not using let's say a basic or naive random walk approximation or sampling just the skeleton of this subordinator? Well, if you had the skeleton only on this grid, and you stop the first time you cross, obviously you need to stop one step before crossing, because you need to, the process must not exceed value t, then you get a biased algorithm, right? So the Monte Carlo estimator is now biased. The bias is proportional to this quantity here shown on the screen. And for the L2 error to be smaller than epsilon squared, it means for the estimator to be very close to the actual value, you need both the bias and the variance to be small. Okay? This results, the quotient of the complexities is basically proportional to 1 over h, which is proportional to epsilon to the minus 1 x squared e to the t alpha. Dependence in this case in epsilon and in t is particularly bad. It's an entire whole order of magnitude apart from the usual Monte Carlo, where you have exact samples and it's just epsilon to the minus 2. And in fact, the complexity also blows very delicately in t because it's exponentially increasing, right? So this gets worse and worse the longer the time horizon, the longer the t, the domain in t is. So this is already, I think, good enough justification for why you want to get exact simulations. But what else can you get out of it other than just FPDEs? Well, you can extend the algorithm for certain processes of bounded variation. This is an extension actually that G had already developed in his paper. If you consider a process Z that can be decomposed as Z plus minus Z minus, where Z plus is this temperate stable subordinator for which we can sample the crossing, driftless in this case, and Z minus is any non-decreasing Levy process, so possibly Cambon-Poisson or a subordinator. Then you can also sample the crossings of Z across constant barriers. Okay, so I'll explain the idea for more general barriers, and I'll explain also where the problem arises and why we need to focus on only constant barriers. Okay, so the idea is that the crossing of the difference process Z is a subset of the crossings of Z plus. Okay, so essentially we just need to sample a crossing of Z plus, and at the time of the crossing determine if this is also a crossing of Z or not. How do we do this? We simply have the crossing of Z plus, and we subtract the increment over this time horizon of the subordinator or the process Z minus. If the increment was not large enough to take you below the crossing, then it's a crossing also for Z, and if it does take you below, you just need to restart the procedure again. So this is essentially what this bullet point says, and I will now give you a figure. Okay, so consider this barrier, and you have your subordinator Z plus. You find the first crossing, and now you need to sample Z minus over this time horizon, the increment of Z minus over this time horizon, to determine if this is also crossing of Z. But in this case, it isn't a crossing of Z. It takes you all the way down, so now you need to repeat the process and fish for the next crossing time. And this is what you do. You find another crossing time, and now you need to see if the new increment will take you below the curve or not. And oh la la, it doesn't take you below the curve. You're still above, and that's great because that means that this is the crossing of Z as well, right? And you can work out the value of the jump. it's going to be precisely of this size. Yes. So the jump is going to be of this size, obviously, because the z minus does not jump, and this is the final value. So that's it. Okay, that's what you need to know. Now, what can go wrong? Why can z plus not have a drift, or b be anything other than just a constant barrier? Well, in this case, let's imagine this b that is strictly decreasing. There's a chance that the difference, so z, that's the difference of z plus and z minus, creeps across the boundary function. In fact, there's a positive probability that this occurs for any function that, for any b that is not constant, as shown by both Chi and Loic Chaumont in his student PDEs. So when this occurs, this procedure that I just described cannot possibly detect the crossing. That's because z plus, you're getting the successive crossings of z plus, but at each successive crossing, you still need to do the update for z minus. And this update will always take you down so long as z minus contains either a drift or is of infinite activity. So unless you're dealing with only subordinator minus Campan Poisson, this will not work in general for with probability. This will not stop with probability 1 for all boundary variation processes except the ones I just described. Okay, so leaving those details apart, how can we use this for other things? So, for example, you can use it to price barrier options, certain barrier options. So, in the case of an up and out barrier call, the payoff, the asset, risky asset, is modeled by R0 times e to the xt, where xt is the boundary variation process, and the payoff is of this form, basically something dependent on the final value minus k. This hockey stick function, and only paid if the path supremum did not exceed some level m. Some algebra later, we can show that it's equal to this payoff, where tau star is the minimum between crossing time and capital T. So capital T, note here, is can also be introduced here in the algorithm very easily. So at any of these aggressive crossings, I can simply also stop if the crossing time occurred after capital T, and then just sample the marginal for the time that it's left. And so this is very easy. And once you get this running and you get your Monte Carlo estimator, you can get these very nice functions based on simply 10,000 samples. All right. In here we consider no discount rate, but including the discount rate is completely easy. So there's no further problem. So I hope you can use this algorithm available on the GitHub repository in the description, and you make use of it to your liking. If you're interested in how the algorithm works and how it's constructed, you can also stay tuned for the next video. Thank you and goodbye.